All right, welcome to The Explainer. Today we are diving headfirst into the world of signals. Now, they're one of those things that are absolutely fundamental to how operating systems work, but let me tell you, really mastering them is a whole other level. So let's get into it.
It's funny. Kind of like George Costanza, we see signals all the time without really getting what's going on under the hood. In the programming world, a signal isn't a social cue. It's what's called an asynchronous software interrupt. It's a message, right? It could be a gentle tap on the shoulder, or as we'll see, it could be a hard shove to a running program.
Okay, so the best way I've found to think about a signal is to picture it as an uninvited messenger. It just shows up at your program's front door, totally unannounced, and it demands attention, like right now. Your program has absolutely no choice but to stop whatever it was doing and deal with this sudden interruption.
I mean, think about it. You've definitely done this. That program freezes up, and what's the first thing you do? You mash Control-C, right? Well, congratulations, you've just sent a signal. You sent a direct message to that process telling it, hey, stop what you're doing. It's an incredibly powerful backdoor for us users when a program just stops listening.
So we have this messenger, but how does it actually get from, point A to point B? A signal has this whole life story, a journey it takes from the second it's created until it finally arrives and forces a process to react. Let's trace that path.
So first, it's generated. It just pops into existence, maybe from you hitting Control-C. Then it enters the pending state. It's basically just waiting in line for the kernel to give it the green light. And finally, the kernel delivers the signal. The second that happens, the receiving process gets interrupted, and it has to deal with it.
And let me tell you, these messengers, they all have very different personalities. SIGINT, that's your Control-C, it's like a polite knock on the door. SIGTERM is a bit more serious, a firm request to leave. SIGSTOP is like yelling freeze, and SIGCONT is the okay, you can go that follows. And then you've got SIGKILL. That's not a knock. That's the door getting kicked clean off its hinges.
So the messenger's at the door. Now what? Well, the program actually has some choices. It doesn't have to just roll over and do what it's told. It gets to decide how it wants to answer that door. And this, my friends, is where things get really interesting and maybe a little dangerous.
This rulebook has a technical name, the signal disposition. For any signal that comes its way, a process can do one of three things. It can just do the default action, which a lot of the time is just to terminate. It can choose to completely ignore the signal, or, and this is the powerful one, it can run a custom piece of code called a signal handler to do something very specific.
But, and this is the really, really important part, because signals can happen at any time. They can show up at the absolute worst possible moment. They can interrupt your code right in the middle of a super delicate operation. And when that happens, you can get chaos.
All right, picture this. Your program is right in the middle of a delicate task. Let's say it's writing the word hello into a shared piece of memory. It's gotten as far as HEL, and then, bam, a signal gets delivered. Your program is frozen right there, mid-word.
The signal handler jumps in, does its thing, in this case, writing world to that exact same spot. Then, when the handler's done, control goes back to your original function. But everything's a mess. The data is totally corrupted. What was supposed to be hello is now world. This is a classic re-entrancy problem, and it is an absolute nightmare to debug. So how do you avoid this mess? Well, the smart way, the safe way, is to make your signal handler do almost nothing. Seriously, the best practice is for the handler to just flip a switch, to set a little flag. You use a special type of variable for this, a volatile sig_atomic t, that's designed to be safe from these kinds of interruptions. The handler just sets the flag, and then the main part of your program checks on that flag every now and then to handle the cleanup in a safe, controlled way. Okay, but what if you have a chunk of code that is just so important, so delicate that it cannot be interrupted under any circumstances? Well, you can basically hang a do not disturb sign on your program's door. This do not disturb sign is called a signal mask. Think of it like a bouncer's list for your process. The kernel, before it delivers any signal, checks this list. If the signal's on the do not disturb list, the kernel just says, okay, not now, and the signal has to wait in the pending queue until the program says it's okay to come in. And that's why signal masks are such a game changer. They let you carve out these little safe zones in your code, these critical sections.
Inside that zone, you can do all the sensitive, delicate work you need, with the peace of mind that no uninvited messenger is going to burst in and wreck the place. All right, now let's talk about the big one. The messenger you can't ignore, the one you can't block, the one that doesn't knock, it just kicks the door in. This is the signal you use when all else fails. Look, using Kill 9, which sends the SIGKILL signal, it's brutal. The process gets zero warning. Zero. It can't clean up its temp files. It can't shut down its network sockets nicely. It can't even say goodbye to its child processes. It is just instant, messy, digital death.
I absolutely love this quote from the source material because it just hits the nail on the head. Using SIGKILL for a simple problem is like, yeah, it's using a combine harvester to do a little light gardening. It's total overkill and you're going to make a huge mess.
So here's the big takeaway. The thing you really need to remember. Always start gentle. Use SIGTERM, that's Signal 15. It's the firm request. It gives the process a chance to clean up and shut down gracefully. Only when a process is truly, completely stuck and ignoring you should you even think about reaching for the nuclear option, SIGKILL, which is Signal 9.
And that really gets to the heart of it, doesn't it? Signals are this incredibly powerful fundamental tool that gives us control over our systems. But as we've seen, that exact same power can create some of the most subtle, frustrating bugs or cause catastrophic failures if we're not careful. That uninvited messenger, well, it's a necessary part of the system, but you'd better be ready for it when it comes knocking.